Good morning, everybody. Let's start today's lecture with a quick review of the things that we did last time. Remember, we were doing virtual memory and paging. Paging was the answer to many problems for the memory abstraction of address spaces. The basic idea of the paging is divide your virtual address space into chunks called pages. Usually these are 2 kilobytes, 4 kilobytes of memory pieces. And when you produce a virtual address on the fly while during the execution in a half a clock cycle, translate that address from virtual address space to the physical address space. Okay, that's the idea. So how do I do that? I keep my virtual pages in a page table, okay, and sorry, I keep my physical page frames in a page table. When I get the virtual page address, okay, like this one, I look it up into this page table in a very quick amount of time, okay, and I find the result and I replace this part. I replace this 4 bits with 3 bits. So my 16-bit of virtual address space becomes just 15-bit of physical address space. Okay, so that's the basic idea. But things are not that simple. The thing is, these page tables are not as small as like 16 element tables or arrays, right? They are much larger. Last time we did the calculations, okay, we are talking about 1 mega elements of page tables, right? So that's not going to work. We need to do something. Of course, I need to keep the page tables in the RAM. That's one thing. If I keep using them in the RAM, that's going to be very slow because every time I make a virtual to physical address translation, it's going to take 2 memory references. I don't like that. That's going to make my programs 2 times slower compared to other approaches. So we need to come up with something. So the answer is translation look-aside buffer. It's like cached version of the page table. Okay, so my translation look-aside buffer is a small cached portion of the page table. I only keep a limited amount of page table entries here. Okay, page table entries here. Indexing is done by the virtual page. I asked the question, do you have the virtual page number 20? It says yes. It says yes. And when it says yes, so what is the page frame for that? It's 38, so I got it. Okay. But the thing is, of course, I can't keep everything in this table. This is too small. So how does it work? Well, principle of locality says that for an average program, I can get a hit rate of 99%, and that's going to be good enough for me. Okay. And why are we looking at this? Okay. Question for you, maybe. Where's my pen? Where is my pen? Okay, pen. So we know that um, there is a, if this is my CPU, okay, and if this is my memory, I know that in my CPU there is a level 1 cache, level 2 cache, level 3 cache. Let's say this is level 1 cache. So between CPU and my memory, okay, between CPU and my memory, there is level 1 cache and other 2 caches too. Okay. How come we never talk about how to manage the data inside the cache in the operating system. For example, when we talk about this memory stuff. We talked about the hierarchy of the memories and etc. We are talking about this inside the MMU, inside the CPU. I have this MMU. We are talking about the structure of the MMU and how to keep the data in MMU, right? But in this book, there is no discussion of how to manage the cache between CPU and the memory. Why don't we talk about it? What should stay inside the cache? What shouldn't? And how should be the cache replacement algorithms? Anybody has any answers? Well, you might say, well, I didn't write the book. Yeah, that's true. But that's an important thing. Maybe we should go back and we should talk about the TLB a little bit. Many risk machines do nearly all of this page management in software. Okay, that's why it becomes a topic of operating system. Cache stuff is handled by the hardware. Okay, that's why operating system doesn't deal with it. Operating system most of the time doesn't know that how much memory is in cache and how much memory is in the memory, what is my cache hit rate, what is my replacement algorithms, and etc. It is all done by the hardware. That's why we don't talk about it. But MMU, okay, and the TLB, as the book says, most risk machines, risk-based machines, even the hybrid ones, they handle the MMU stuff, TLB stuff by the software, which means it is the operating system. That's why we talk about it. Okay, so we talked about software TLB management and a few definitions here, soft miss and hard miss. Okay, we don't like hard misses because when a hard miss occurs, okay, the page is not in the memory and I have to load it back from the desk. That's going to take very long amount of time. We don't like hard misses. Soft misses are not good, but they are not as bad as hard misses. Soft miss means that the page I am looking for is not in the TLB, but the page is in the memory. All I'm going to do is just update my page tables and TLB, and I am done. Okay. So and these are this red line I don't like, right? That's the hardest hit, hardest. That's the hardest miss that you are going to that you are going to have. I like this orange line here, orange path. It's good. It is in the TLB and I got it. Next, I like this blue one. It's a soft mess. Okay, so we talked about those. And we said that TLB solves lots of these problems. Remember, page tables cannot fit in the memory. The page tables cannot fit in the TLB. So I have to keep only a small part of it in the MMU. Rest of them will stay in the CPU, memory. But the thing is, the page table is still very large. Okay, page table is still very large. Why? Because we are talking about a memory address space of 2 to the 48. Okay. That's a very large address space. Let's look at this one. So, guess this chat. What is the Now I need to, okay, what is the largest virtual memory space for Linux and Windows? Run. Okay, I need to reload it maybe. Do you guys know what's happening? Why doesn't this work? Come on, you are the Chat GPT expert. Unable to, oh, it is, everybody is doing it, okay. Okay, so for 32-bit systems, we don't have that many more, okay. So it is 4 gigabytes because it is 32-bit, but for 64-bit system, 4-level page table structure, maximum is 256 terabytes, okay. If my page table, okay, if my, okay, so this is 64-bit system. 64-bit means that 2 to the 64 is my maximum hard disk space. That will correspond to this much. Okay. If this is my virtual memory space, nobody has this kind of memory, right? I mean, nobody has a memory size of 256 terabytes on a normal computer. Okay. For a normal computer, at most you are going to have maybe 32, maybe 64 gigabytes. Okay, not even 1,000 of this. So, but I have to handle this. And by the way, this is for each process. Okay, this is for each process. That means that if I have hundreds of processes, there is no way I can deal with this. Of course, we know that, but I have to keep the page table somewhere. So where am I going to keep this page table? The page table for this kind of an address space is going to be gigabytes large. Okay, I can't keep it. I can't keep it in my physical memory. Okay, that's why I have to find something. For Windows, again, for 32-bit system, it is 4 gigabytes. For 64-bit system, virtual memory is the theoretical limit is 16 exabytes. Yeah. No, well, no, you are not going to reach this, but theoretically, this is 16 exabytes. Whatever exabyte. Exa is one upper than the, no, exa is larger than the petabytes, right? Terabytes and the petabytes and the exabytes. Yeah, so this is using the whole 64-bit system thing. Okay, 2 to the 64. Let's see. Let's see. Let's see. Um, this is kilo, mega, giga. Okay, tera, peta. Yeah, and then 60 is exa. And 64-bit is, yeah, 64-bit is really, it is like 16 exa. It is using, so it is using the full 64-bit of it. Okay. And it looks like Linux is using this 2 to the 60, 40, 46 at the space. Okay. So the point is for both operating systems, this page table is too much. I can't keep it in my physical memory, so I use multi-level page tables. This is what I do. I divide my 32, in this case, 32-bit addresses into 3, page table 1, page table 2, and page table 3. The first 10-bit is page table 1. First, I make a lookup in the top level page table, which is, since this is 10 bits, my page table is going to have 2 to the 10 elements in it, 1 kilo elements only. Okay. If the page that I am looking for is in this page table, then I find the address of the actual page table somewhere in the memory. For example, it is this one, and I take the next 10 bits and I use that as an address for this one. Okay, and this one will give me the real page frame number. Okay, so this way I keep only these two in the memory, just 1 kilo elements, 1 kilo element, that's 2 kilo elements, instead of keeping this many 2 to the 20 elements in my memory. 2 to 20 is 1 mega element. Okay. Instead of 1 million table entries, I'm just keeping 2000. And principle of locality helps me keep the rest of the page tables on the desk. Okay. On the disk, I can afford to have gigabytes of space, because disk is a very large space than the memory. Okay, so by the way, this was for a very simple computer. For today's computers, for the Linux case, for example, this is the case. I have 1, 2, 3, 4 levels of, what did ChatGPT say about the Linux? It said 4-level page table structure. Okay, so 9 bits, 9 bits, 9 bits. So the top level is just 512 entries, then 512 here, there. So in my memory, if I am lucky, if I am working on the same memory positions, okay, it is only 1000, 2000, and it's like 2500 entries in my memory. If I am lucky, if I keep working on the same parts of the memory, this is how many entries of page table I am keeping in my physical memory. Of course, most of it will be in my TLB. Okay, most of it will be in my TLB. Good. Any questions? If there are no questions, let's look at this. Let's look at another solution for the large page table sizes. It is called inverted page tables. Okay, so the idea is this. Let's look at this very simple case. Let's say I have a virtual address space of 16 bits. Okay, so it is 2 to the 16 is my address space, with the 4 kilobytes of pages. Okay, it's going to be 2 to the 4 elements inside my page table. Okay, so 2 to the 4 elements is this. 8. Now I have, here is 16. This is my page table. Okay, and let's say my physical memory is only, this is virtual and this is physical, 2 to the, let's say, 14. Okay, if it is 2 to the 14, then I am going to have what? How many pages do I have in my physical memory? It's going to be 2 to the 2, right? It's going to be just 4. like this. This is my physical memory. Very, very limited physical memory. Okay, this is physical memory. Usually, this is what I do, right? Usually, when I say, okay, I am going to access some part of the memory, but I need to look it up it from the page table. I follow this link, right? Okay, that's good enough. I would say this part lives in this physical page frame. Inverted page table says that, well, I mean, most of this table will be empty, right? Only 4 elements can live in it because I have only 4 of them. Okay, only 4 of them. So why don't we do this? Keep a page table. Keep a page table. Only this many elements with this many elements. This is an inverted. This pen is not good. Let me change my pen. It's a better pen. Inverted page table. Okay. Inverted page table keeps the number of elements inside the inverted page table is the same as physical memory page frame size. It's the same thing. When I make a let's say virtual address to physical address lookup, let's try to do that. Let's say this is my virtual address. The first 4 bits, okay, this part is my virtual bits. I take these 4 bits. 4-bit means that 2 to the 4 is 16. 16, I need 16 elements, but I don't have 16 elements. So I take this number here from here, so that V number, and I use a hashing function, to map it to just 4 numbers. Okay, so inverted page number. So hashing could be as simple as this number could be at most 16, right? The hashing could be, let's say, HV is equal to V modulo V modulo 0, 1, 2, okay, 1 or 0 modulo 4. Okay, so you get this number, take the modulo 4. Okay, that will give you the inverted page table number, and you are going to get your frame number from there, and it will link you somewhere. Okay, so what is the problem with this approach? It is very simple. Page table size is the same as the number of frames, number of page table entries is the same as your physical memory page frame size. Okay, 4 frames there and 4 elements there. Okay, very nice. And I use a hashing function like this. Map this virtual address by taking the modulo of it. Remember, V could be at most 16. So 16, V could be at most 16, but we are going to start from 0. 0 modulo 4 is 0. So so it's going to be 0 will be mapped to 0. 1 will be mapped to 1. 2 will be mapped to 2. 14 will be mapped to what? 14 will be mapped to, take the modulo 2. What?
2.
2. 15 will be mapped to 3. There is no 16, right? So everybody is mapped to something. So what is the problem? The problem is Same problem that we have with the hashing. The problem is what? Those people who took the data structures course,
Different elements point to the same place.
exactly. Who said that?
Me, Burak.
Okay, so Burak, yeah. So exactly like this one, 2 and 14 are they are pointing to the same place. Okay, so if this one is 0, 0, 1, 0 or 1, 0, 1, 0, right? It is pointing to the same location. I don't like it. How am I gonna find it? I mean, both of them. So that's what you do. I mean, in the hash cases, this can happen. It is called collisions. And how do you handle the collisions in the hash tables?
We can use double linked lists.
Yeah, we can put a linked list in here. We say that, okay, this is my first entry. This is my second entry. Once you know where your page frame is, you follow this linked list, and after that you will say that, okay, I found mine. So it requires you to make a search in this linked list. But luckily, the whole operation can be done in O1, right? Because you learned the data structures course. So if it is done in the hardware, this is all nice. So it is called inverted page tables. And if I am, well, of course, this is not done in hardware. Hardware is going to help you, but not done in hardware. So inverted page tables is an alternative to multi-level page tables or regular page tables. It uses the hash function for the collisions. It uses a linked list. Sometimes it uses open addressing. Okay. But at the end, you need to make a small search and you find it. So if your TLB is large enough, if your hit rate is good enough, then this inverted page table is a very good solution to keep a fraction of memory required for the page table. Okay, so it's inverted page table. But this is a good example again. Let's say you have a 64-bit computer. You are using the whole 64-bit for physical virtual memory addressing. Do you guys hear me?
Yes.
Yes.
Yeah, there was a power outage at the campus, so I am back. What's going on? Oh, what? Okay, I'm getting it now. We are getting the generators to be, yeah, good. Okay, so 64-bit computer, okay. My page sizes are like 4 kilobytes, so it is 2 to the 12. That means what? I need 2 to the 52 page table entries. Okay, this is a very large page table. Okay, this is a very large page table. We are talking about 4 peta entries, 54 peta entries, right? 54 peta entries. You can't fit in this into any memory. Okay, so what are you gonna do? Let's use the inverted page table. If my physical memory is 1 gigabytes. That means what? It is 2 to the 30 bytes, and with the 4 kilobyte page frames, it's going to be 2 to the 18 entries in my inverted page table. Okay, so but each list. Okay, and if you compare this structure with this one, it is obvious that it has definitely a very large memory advantage. But nevertheless, the Unix and the Windows operating system doesn't use this scheme. They use the multi-level page tables, as we looked at before. Okay. Good. Any questions so far? Any questions?
Sir, can you give an example with the numbers on the pages? I didn't quite understand how the inverted one works.
Well, I think I did this one. Okay, let's do this in our trusty old example here. Okay. So, let's do this exactly. Let's do this exactly the same thing. Okay. Here I have 16-bit of physical virtual address space. Okay. 16-bit of virtual address space. Let me insert a page. Insert a page. Yeah, here it is. Insert a page here. No, just one. Okay. Let me keep both of them on the same page. Okay. So we are doing the same thing. 16-bit virtual address space. So it is 2 to the 16, right? And 15-bit physical address space. Okay. So it is 2 to the 15 is my physical address, physical memory size. So this is again 64 kilobytes. This is 32 kilobytes. Okay. So if I use the regular paging, this is how many entries I should keep in my page table. How am I going to calculate that one? 2 to the 16 over 2 to the 12 is 2 to the 4, which is just 16 elements. It should have 16 elements in it. But with the inverted page table, I keep just 8 elements in it. Okay. So this is my 8 elements. This is inverted page table. And this is my physical memory. And this one has 8 pages too. So how is the translation will be done? It will be done like this. Get your 16-bit address. Let's make this 16. Okay. And I need to translate it to a 15-bit address space. So, but my virtual part is the first 4 bits. So this one, this bit, this bit, this bit, and this bit. This is my virtual bits. And rest of them will be my offsets. V and O. Remember this? V and O. My virtual, divide the virtual address into V and O parts. It's exactly the same thing, V and O, okay? So I take this part, okay, those 4 bits, and I need to map this 4 bits into this 8 element inverted page table. Let's say these 4 bits are 1 0 1 0. Okay, 1 0 1 0. It makes 1 2 4 8 8 plus 2. It is 10, right? This one is 10. Okay, so V is 10. V is 10. So I do this H10 is going to be hash table of 10. 10 modulo what?
4.
Is it 4?
8.
8. It is 8. Why? Because I have 8 elements in there, right? I have 8 elements there. So it's going to be just 2, right? So this will be my position here, 2. Okay, I have a linked list pointer in this one. The first one says that, okay, I am a page table entry, and my virtual page number is 10, or maybe, oh, okay, maybe I should do this. I have 2 elements in there. Okay, it says my virtual 4 bits is 2, and 2 is going to map me somewhere here. The second one says that my virtual bits is 10, and this is going to map somewhere here. Okay, why do I have 2 in here? Because both 2 and 10 will map to the same location here, because 2 modulo 8 is 2, 10 modulo 8 is 2, right? Both of them are the same. So both of them will map to here. And if I follow this linked list, I will find that 2 lives here, 10 lives there. Okay? So this is how it works. An example. So I gave you an example for the collision too. Did I answer your question, Burak? Was that your question, Burak?
It was my question.
Abdullah, yeah.
Yeah,
Okay.
Also, I wonder why the entry with the number 2 isn't in the second position.
You mean here? You mean this part?
Yes.
Well, because this is my inverted page table address that way, right? It is 0, 1, 2, 3, 4, 5, 6, 7. Out of hashing, the only numbers can come are 0 to 7. Okay. So I converted this 10 into a number between 0 and 7. Okay.
Okay, I get it. In my
Okay.
head, I put the 0 at the top.
Oh, okay. Okay. This page table. I think I was
Thank you.
trying to use it the same format in here, because it was like that too, right?
Okay, thank you. I got it now.
Okay, good. Okay. So the hashing doesn't have to be done this way. There are many ways to hash it, but I mean, depending on how you do the hashing, the collision numbers might increase or something like that. But this is the simplest hashing that you can do.
Sir,
Okay. Any other questions?
I would like to ask another question.
Okay,
You said,
good. People are asking questions today.
Windows and Linux
Yeah.
don't use inverted pages.
Yeah.
They prefer multi-level pages.
Yeah.
Why?
I don't know. Let's
That's a
ask.
company policy.
Let's no. Well, I mean, no. I mean, the company policy doesn't mean that they should do something stupid. Why doesn't Linux use inverted page tables? Okay. Inverted page tables are typically used in systems that have large number of processes with smaller disk spaces and optimized for systems with limited physical memory. Well, yeah. Linux is used for these kind of cases too. Okay, and Linux is a very widely accepted operating system from the simplest devices to the very large devices. Doesn't answer is it very nice, but that's the answer. So instead, the Linux uses the hierarchical ones. So how do you decide that if you are designing an operating system, how do you decide that you should use multi-level page tables or the inverted page tables? There is no closed form formulas. There is no analytical calculations. I take the derivative of something and I run some differential equation and I find the answer. No, it doesn't work that way. All you do is just you run simulations. Okay, you run simulations. Okay, you run your operating system on a simulated platform. You implement both inverted page tables and the multi-level page tables, and look at their performance in terms of how do you measure the performance of your virtual memory addressing by looking at the number of memory accesses, right? The latency, and by looking at the memory that you use. If you are after definite CPU time, I need better CPU time. You may prefer one technique over the other one. So usually the answer to these questions come to the answer to these questions come to after running some simulations. Well, inverted page tables, they seem like very nice solutions. Multi-level page tables are not bad either, right? They are not bad either. And I know, Ömer Faruk, what you are thinking. You are thinking that in the multi-level page tables, somebody has to store this much information somewhere, whether in the main memory or on the disk. But what we are missing here is that most of this virtual address space is empty. Nobody is using it. If some part of it is completely empty, you don't have to keep it anywhere, okay? You just keep that information. This part of the, let's say, this part of the memory is not used at all, okay? You don't keep it in the memory, okay? You just use a flag like this one, okay? Like, where is my, yeah, okay? You will say that this one is none, this one is none. What does that mean? That means that I don't keep those page tables. They are not valid. I am not using them. My process doesn't need that many pages. Okay? So this is very flexible. As I said before, I keep most of my page table entries in the TLB anyways. So this is efficient both in terms of memory and this space, whether it is a disk space or the physical memory, and it is efficient in terms of access times. Okay?
Thank you, sir.
And maybe I should ask this question. Maybe I should ask this question. Give an example. Give an example OS that uses inverted page tables. Solaris, it's a Unix-based thing. Well, again, I am not sure if this is correct. Solaris was the flag holder of the admiralship of the Unix world for maybe 10 years in 1980s and 1990s, maybe. Okay. Later, Oracle bought all the rights for the Solaris system. By the way, some microsystems, they invented the Java programming language. Okay. So I say that it's a Unix operating system. It uses inverted page tables. I am not sure if it is correct, but that means what? It means inverted page tables are usable in an operating system like Unix. Sometimes we don't have good answers for these kind of questions. I mean, mostly historical. And at the beginning, somebody decided that let's use the page tables. Well, these are getting larger, so let's use the multi-level page tables. So going from the regular page table to the multi-level page table is easier than going from regular page table to the inverted page table. Okay. Good. So let's go back. Multi-level page tables, we talked about those, and we talked about inverted page tables. Okay, so far we talked about the structure of the page tables, but we ignored the main question, the toughest question. Okay. I have 16. I have here 16 virtual pages, but in my physical memory, I have only 4 physical page frames. Okay. I need to keep some part of this whole virtual memory on the desk. Which part I am going to keep in the desk? Which part I am not? So let's say this one is not on the memory, and I need to get it from the disk to the memory. And my memory is full. My memory is full. It is all full, okay? So which one should I replace? Should I replace this one, this one, this one, and this one? Okay, the one that makes this decision is called page replacement algorithm. It's like scheduling, right? 4 processes are ready to run. Which one should I schedule next? Okay, so that's the question. And for those, we have scheduling algorithms. And this one is similar. I need to replace one of these pages. Which one should I replace? Okay, which one should I replace? And that's called page replacement algorithm. Okay, page replacement algorithm. We are going to look at those. The first one is the optimal algorithm. It is really optimal, and it is not implementable. It's a theoretical algorithm only, because the optimal algorithm needs to see it in the feature. Optimal algorithm needs to see the feature first. After seeing the feature, you say that if you replace these, this will be better. So optimal algorithm is only good for comparing your algorithm with it. If your algorithm is doing similar to optimal algorithm, it cannot do better than optimal. If you are doing similar to optimal algorithm, then you are good. Okay. Then we are going to look at the others. At the end, we are going to see that this one, and maybe this one. These are only for educational purposes. These are going to help us understand how they work. The best algorithms are these two. Linux and Windows, they use these algorithms for the page replacement. Okay, so let's discuss those, but before that, let's take some break. Let's be here around 9:35. Okay. 15-minute break.